This conference will now be recorded.
Very good evening, students. Today we'll be discussing polarization of light. So this is the last portion of the wave optics chapter. So in this class, what we are going to discuss is, first I'll give you introduction. So these are the contents in this lecture. I'll give you a brief introduction. What is called polarization, or is there any real life examples of polarization effect of light? Why polarization is seen only in transverse light, etc. Okay, transverse wave. Then I'll discuss about polarized light, unpolarized light, and then type of polarization we can have, and the device which is called polarizer is used to polarize and unpolarized light.
This conference will now be recorded.
Hello students, we are back with another topic of wave optics. Today we'll be discussing and learning about polarization of light. So these are the contents for today's lecture or today's session. I'll give you a brief introduction about polarization of light. Then I'll discuss what is a polarized light, how to pictorially or represent this unpolarized light, and then I'll talk about polarized light and different types of polarization. Then I'll discuss about the device which is used to polarize unpolarized light, so that is called polarizer. And then we'll see a demonstration how using a polarizer we can polarize an unpolarized light. And then finally I'll discuss Malus law in today's session. So without much delay, let us go to the original discussions. So see, polarization is also a characteristics property of waves. Okay, characteristic property of wave. See, polarization okay, so polarization, this can be written as Z or S, whatever it is. So polarization is observed only in case of transverse wave. Okay, transverse waves. Okay, see, reflection, refraction, interference, diffraction, these we have discussed, and we have seen that reflection, refraction, interference, diffraction, these phenomena are observed in any type of waves, like sound wave also exhibits in interference as well as diffraction, and reflection, diffraction is obviously happening in case of sound wave also. But polarization is only observed in case of transverse waves. That's why electromagnetic waves which are naturally occurring transverse wave will see polarization of transverse waves, of light today. Okay, transverse wave, light is transverse wave because it is electromagnetic wave. You look here, electromagnetic wave consists of two quantities. That one is electric field, another one is magnetic field. And as we have discussed in the electromagnetic wave chapter, that these electric field vectors and magnetic field vectors, they are oscillating perpendicular to each other. You look this if I say this is y-axis, this is x-axis, so B is oscillating. See, B vector, magnetic field vector is oscillating in the x direction, and electric field vector is oscillating in the y direction. So they are mutually perpendicular. So B is in xz plane, and electric field is oscillating in the yz plane. So these are two mutually perpendicular direction. Okay, electric field and magnetic field, they are oscillating perpendicular to each other, and they are oscillating in a direction perpendicular to the direction of propagation. So here wave is progressing in the z direction. Okay, say E cross H or E cross B gives K. Okay, the proportionally you can say some constants will be there. Okay, so you know E cross B gives K. This is the direction of propagation vector. Okay, direction of propagation vector. So you know what, yeah, I should take E x to y is equal to z. Okay, I shouldn't take B along the x-axis. Then if it is propagating along z direction, then this should be x direction and this should be y direction. Okay, there is a small correction here. So see, it is I cap cross j cap. Ij gives k cap. Okay, so that's all. So see here, electromagnetic wave is propagating along z direction, and electric field vector is propagating in a direction x, so which is perpendicular to the direction of propagation, as well as y is also perpendicular. Y, see, y is oscillating in a direction perpendicular to the direction of propagation of the electromagnetic wave, which is z direction. Okay, all right, so you might be thinking why I'm saying this thing. Okay, I'm saying this because I need to tell you that the wave which has transverse characteristics or which is transverse in nature will only exhibit polarization. Okay, so that's why I'm saying this thing. Now one more good information I can give you, like say among this electromagnetic wave, electric field vector, okay, electric field vector alone is responsible for our vision. This is very important. See, we observe, see, we see light, isn't it? We see light. Light is an electromagnetic wave, but among these two vectors or two fields, electric and magnetic fields, electric field alone is actually electric field vision. Okay, so electric field is alone responsible for vision. Okay, vision. So electric field alone is responsible for our vision. So that's why when you see light, we see only the electric field vector only. Okay, when you see light, that means we are seeing only the electric field vector. Okay, or electric field alone we are seeing through our eyes. Okay, one more point is that, see, okay, so we are learning polarization of light, but I have not spoken what is polarization. Okay, I'll tell you, this is the special property of light or special property of transverse wave, transverse electromagnetic wave, that the electric field, since vision is possible due to only due to electric field vector, I'm just talking about now. When I will be talking about polarization, I will be talking about only electric field vector. Okay, electric field vector alone I will talk about. Okay, while talking about polarization, I'll talk about only about electric field vector. Okay, because electric field vector is responsible for our vision. Now, this electric field vector has a tendency, or it, see, polarization is the property of light, or it is the phenomenon of light that it can vibrate or oscillate. Electric field vector can oscillate in a particular plane or in a particular direction. Okay, in a particular plane or particular direction. That means light can be confined in a plane, in a particular plane, when you will not be able to see this light from the other plane. Suppose if the light is, see, if the light is actually confined in some xy plane, then you will see alone in this xy plane. You will not be able to see this in some other plane. Okay, and see, we do see the effect of polarization of light in our real life. Okay, suppose you have, see, if you have gone uh, for a trip in the beach, you can see in the water surface. Okay, or this is very much visible in the quiet surface of the water, some places of the surface will be too much glaring compared to the other portions. Okay, compared to the other portions, and that glaring of the water surface will be seen from a particular direction only. You will not see from other direction. You may not see from this direction. You will see alone from this direction. Okay, that means what? Electric field is oscillating in a particular plane, and through that plane you are looking. Okay, or towards that plane you are looking. That's why you are seeing that glare, okay, or glossiness of the surface of the water. Okay, I hope you have experienced this, that particular point or particular portion of water surface is looking very, very glaring, and that is because of the light, polarized light, which are coming into your eyes. Okay, but if you just change the angle of your sight, you may not see this portion again glaring, isn't it? This is actually polarization, because light wave will be oscillating in a particular plane. Okay, so, or this is called localization. Okay, so light wave or localization of light wave is, or electric field vector localization or confinement of electric field vector in a particular plane is actually polarization. Now I'll come to the next point. So what we have discussed here, what is polarization? Polarization is actually confinement or localization of light in a particular plane, and polarization occurs only for, or polarization happens or seen in case of transverse wave, alone. Okay, transverse wave alone. Okay, and we have seen that E is responsible. We have discussed this, responsible for our vision. Okay, and we have discussed that polarization means localization of light wave or electric field vector. Local polarization, localization of light, or we can say E vector, electric field vector, in a particular plane. This is, in simple language, the polarization means. Okay, all right, now we'll see what is called an unpolarized light and what is polarized light. See, light which are coming directly from sun may not be polarized light. Okay, okay, let me define first what is polarization. Okay, polarized light. Unpolarized light. Okay, so unpolarized light is the light which has electric field vector oscillating or vibrating in all possible direction or along all possible direction, perpendicular to the direction. Okay, this I can remove from here now. Perpendicular to the direction of propagation of the EM wave, electromagnetic wave. Okay, here electromagnetic wave means I can say the light itself. Okay, propagation of direction of propagation of itself. Okay, it might be propagating in certain direction, right? So light is propagating direction of propagation, direction of its propagation, or propagation of light wave also fine. Okay, so let me explain. The light which has electric field vector vibrating in all possible directions perpendicular to the direction of its propagation. Okay, see, light may propagate in a certain direction like this. Okay, maybe in z direction. Okay, this is z direction. Then if you have a light which has electric field vector oscillating or vibrating in all possible direction in the xy plane, all possible direction in the xy plane. Okay, then this light, see, you can see this is actually pictorial representation of unpolarized light. That means what? It has electric field vector which is oscillating in all direction in a plane. Okay, in all direction. Okay, in all direction. So this is, so these are actually electric field vectors which is, by showing you in all direction, I just want to mean, or it is meant that the light has electric field vector which is vibrating in all possible direction in a particular plane which is perpendicular to the direction of the propagation of the light. Okay, this is actually unpolarized light. Okay, so this is, see, you can see this is polarized light. If it is vibrating in a particular direction, then it is actually polarized light. Okay, see here electric field has many directions. Okay, but here you look, it is vibrating in a particular direction. If I say this is y direction, it is vibrating along y direction. Okay, so this is unpolarized light. Now I'll show you what is polarized light. Let me write first what is polarized light as a definition. We can say if a light the light as a propagation is called an unpolarized light. If a light wave has electric field vector vibrating in a particular direction, obviously that has to be perpendicular to the direction of propagation of the light itself. Okay, then that is called a polarized light. Okay, so if a light wave has electric field vector vibrating in a particular direction perpendicular to the direction of propagation of the light itself, then that light is called polarized light. You look here, So generally, polarized and unpolarized light can be represented by this kind of representation, pictorial representation. See, this particular double arrow line is representing light wave having electric field vector having E vibrating in the plane of the paper, in the plane of the paper or plane of paper. Okay, so this is called electric field vector oscillating in plane. That means plane of the paper, oscillating in plane of the paper. And see here in the unpolarized light, see there are dots, right? These dots are representing the light vector, light wave having electric field vector vibrating in a direction, perpendicular to the plane of the paper. Okay, perpendicular to the plane of the paper. Okay, to the plane of the paper. Here because of less space I'm just saying that. So you can see in unpolarized light there are light vectors which are oscillating in plane and light vectors which are oscillating, electric field vectors which are oscillating out of plane or plane perpendicular to the plane of the paper. Okay, and see if I split this unpolarized light, it can be partially polarized light, it can be completely polarized light. For a completely polarized light, see your light vector or electric field light wave which are having electric field vector oscillating in plane can be separated or will be separated from the light wave which have electric field vector perpendicular which are oscillating in the plane perpendicular to the paper. Okay, plane of the paper. So these are called parallel components of electric field vector. These are called perpendicular component of the electric field vector. Okay, parallel and perpendicular. Parallel component of light and perpendicular component of light. Okay, so this is how, see, in combination this is unpolarized light. When they are separated they are called, so this is also polarized, this is also polarized. Okay, so when you see this, so sometime okay, we'll discuss when situation comes. So this is the definition of polarized light and how to represent the polarized light. We have shown you. See, this is in plane, this have electric field in plane, and these light waves which will have electric field vector, the component of electric field vector in a plane perpendicular to the plane of the paper. Okay, in fact plane perpendicular to this. So these O are actually representing the electric field vector perpendicular to the plane. Okay, this is what it is. Now we'll show you. See, since polarized light, so the type of polarization can be of different type like linearly polarized light or plane polarized light, polarized light. Okay, this is itself called plane polarized light, plane polarized. I'll explain why it is. Plane polarized light. Then we'll have elliptical polarized light. Okay, and circularly polarized light or circularly, elliptically and circularly polarized light. Polarized, okay. But in our syllabus these are not mentioned. We'll just stick to this at this stage, okay, at this syllabus. Like with the syllabus we have only linearly polarized light or plane polarized light. Now I'll tell you why it is called linearly polarized light. Because see, linearly polarized light, they will be oscillating in a particular direction, and since this electric field vector will be confined in a plane, so that's why these are called linearly polarized light or plane polarized light as well. Okay, linearly polarized light means it is oscillating, electric field is oscillating in a particular direction, and since this electric field vector is confined in a plane and then oscillating, that's why this is called linearly polarized light or plane polarized light. Okay, now let us go to polarizer. What are called polarizer, or what is polarizer? As you can say, just device. Polarizer is a device which can polarize unpolarized light. Okay, which can polarize an unpolarized light. So that is a polarizer. So what is a polarizer? Polarizer is a device, an optical device. Okay, polarizer is an optical device. Okay, I'll write here. And a polarizer is an optical device which polarizes which polarizes, in fact plane polarizes. Okay, polarizes or plane polarizes, plane polarization. Okay, polarizes light in a plane polarization. Polarizes an unpolarized light. Okay, a polarizer is an optical device which polarizes an unpolarized light. Okay, the nature of the polarization that a polarizer can have is plane polarized light. Okay, see, polarizer not only is used as a polarizer, it can be used as a polarizer can be used as an analyzer also. Sorry, a polarizer can be used as an analyzer as well. Can also be used as an analyzer. What is analyzer? Which can analyze the polarization, whether a light is polarized or not. See, analyzer will help you. Analyzer helps. Okay, helps one to understand or to check or to understand, okay, to understand whether a light, or to know whether a light is polarized or not. And also, and if the light is polarized, and if the light is polarized, what would the nature of the polarization be? Of the polarization be. Okay, so analyzer will help you to understand whether a light is unpolarized light or polarized light, and then if the light is polarized light, then what is the use, what is the nature of the polarized light, like whether it is line linearly polarized, or it is circularly polarized or elliptically polarized. That also can be understood from this analyzer. So when a polarizer is used to analyze the light, is called actually analyzer. Now I'll tell you that there are different types of polarizer. Okay, I'll tell you few polarizers. So most commonly used polarizers. Okay, one is tourmaline crystal. Okay, tourmaline crystal. Okay, so this tourmaline crystal, will help you to polarize an unpolarized light. Okay, what is this tourmaline crystal at all? This is actually made of, see, this is actually made of boron silicate. Boron silicate. Boron silicate. And it is, you know, it is you see, it is constructed or made in such a way that, see, it actually, what it does, it polarizes the light. So to use this tourmaline crystal as a polarizer, what we have to do, we have to first take a crystal and cut the crystal in such a way that its plane contains a unique optic axis. Then an unpolarized light, upon passing through the crystal normally, it will be polarized light. Okay, see, tourmaline crystal is actually, it is actually made of boron silicate, and this crystal is cut in such a way, this tourmaline crystal will be cut in such a way that it has a definite optic axis. Okay, optic axis, or it is called pass axis also. Tourmaline crystal will have, suppose it is my crystal, it is cut in such a way that it has optic axis along this direction. Okay, along this direction, optic axis or pass axis. Okay, so what happens when a light wave is passing through this? If this is optic axis, if a light is passing through this crystal like this, then see, this light will have two components. If I say light has two components, one along this and another along this direction. So the light wave or vector, see, I have said that unpolarized light is like this, so its electric field vector will oscillate in all possible directions. So the electric field vector which are parallel to the direction of this optic axis, okay, parallel to the optic axis, their vibration is parallel to optic axis. I'll take simplest one. Let me show you. If I have an unpolarized light like this, I'm just taking as a representative one. So this is unpolarized light, UP light here. Now I have tourmaline crystal which has, suppose, pass axis along the y direction. Okay, so I say this is y, this is x, or okay. So anyway, now upon passing through this crystal, you will have only this light vector, and this will be absorbed by the crystal itself. Okay, this which is perpendicular to the pass axis or optic axis, that particular light will be absorbed. Okay, so optic axis or pass axis of a crystal, tourmaline crystal, is that particular axis along which, like, electric field of unpolarized light along this particular direction will pass through the crystal. That means, see, this is unpolarized light, it has both the components of electric field. So through this crystal only this, see, the, like, this will pass through this crystal itself. Okay, because it has pass axis in this direction, so that's why you will get this is polarized light. Okay, so this is about tourmaline crystal. Now we have few more, like you have nickel prism. Okay, nickel prism. Second one, nickel prism. Sorry, nickel prism. Ni prism. Nickel. The word is nickel, not nickel. Nickel prism. So nickel prism, actually this is the name of a scientist. Okay, physicist, Nickel. Nickel prism is an optical device which is used to produce and analyze a plane polarized light. Plane polarized light. It is maybe, oh sorry, it is made by starting to calcite crystal. See, actually nickel prism, I'll just clean this. Tourmaline crystal I have discussed. Now I'll discuss about nickel prism, which is another popular polarizer or analyzer. Okay, so nickel prism, it is actually calcite crystal. Okay, calcite crystal. It is a calcite crystal. Actually, to make a nickel prism, you know, two nickel such crystals will be taken. Okay, and they will be cut in such a way. Suppose they will be cut. Okay, I don't know. So they will be cutting in such a way that so they will be actually cut. I think if I say this is cut like this, so this portion you have, okay, and this portion will be cut like this then. So as a whole you will have like this one portion, another portion maybe sorry okay, like this or something. Okay, so that, okay, so nickel prism is actually made of two calcite crystals, and these two calcite crystals are cut in such a way, in a particular way, and they are sticking together. Look, this, they are sticking together, and this sticking material is called Canada balsam. Okay, this Canada balsam is very famous. Canada balsam, okay, balsam. I'll write once again. So two calcite crystals are cut in a specific way, and then those two pieces will be actually stick to each other by a glue or by an adhesive which is called Canada balsam. Canada balsam. Canada balsam acts as a glue, and when a light actually passes through this, then unpolarized light, it will actually polarize. Okay, I think this happens, this here polarization happens due to scattering. We'll see that scattering action. Okay, scattering operations. Okay, scattering of light. Now another popular type of polarizer is actually available in the laboratory. Those are called polaroids. Polaroids. Polaroid. So polaroids are actually very thin sheets of kind of plastic sheets. Okay, very thin sheets. And when an unpolarized light Polaroid is a thin commercial plastic like sheet which is used to polarize unpolarized light. Okay, it consists of a molecular chain. So this Polaroid actually have a molecular chain. Okay, so what I was trying to say is Polaroid actually a thin plain plastic like sheet used to polarize unpolarized light. It consists of molecular chain. Okay, it consists of molecular chain. If any ray passes through that perpendicular to that chain, then that particular light will be absorbed, and I'm sorry, actually Polaroid will have molecular chain, right? So this molecular chain will, suppose molecular chain in a particular direction is there. when light passes through this perpendicular to this chain also will not so this is okay. So when the light vectors which are perpendicular to this chain actually will be absorbed by the crystal, okay, absorbed by the Polaroid itself. Now we can actually have a small demonstration how using a polarizer and analyzer we can understand whether a light is polarized or not. First of all, how to polarize a light? We can use a polarizer as you see from this figure A. See, this is unpolarized light. If you pass an unpolarized light through a polarizer which has a path axis, see this is the path axis or optic axis. Since the path axis or optic axis in this direction, okay, vertical direction, you can see the electric field vectors which were oscillating in a direction perpendicular the direction along this path axis or in a direction of this path axis. So those electric field vectors will be actually passing through. Okay, now if a light is polarized or not, you can understand even by seeing the intensity. So can you tell me what will be the intensity here? Suppose intensity is here I0 for the unpolarized light. So this is fully polarized light. That means perpendicular component of the electric field is not coming here. Only parallel components which are like a component in the sense like electric field vector which are oscillating in plane. Those are this. Okay. So now only those electric field vectors are there which were oscillating in a plane. Okay, so what will be the intensity? So intensity of the polarized light or linearly polarized or plane polarized light will be half of the unpolarized light. So intensity of the polarized light is half of the unpolarized light. Okay. All right. So by seeing the intensity, decrease of intensity, also you can understand that light is actually polarized or not. So if you see your computer screen and if some portion is actually giving you some clearance, then you can actually see that. But if you use a sunglass or something, you may not see that clearance. Okay, that means you know your light, see the light you see through a glass or spec or a sunglass is actually polarized light. Okay, intensity of the light is actually decreasing in the sunny day. If you go with a spec or a real sunglass, in sunglass what is done, light is polarized in sunglass. Okay, light is polarized in sunglass. That's why you see the half of the intensity of the light which is actually is there or which is actually seen in naked eyes. Okay, now see whether a light is polarized or not, you can understand by taking an analyzer. You can take the same piece of crystal which has identical path axis, so that can be used as an analyzer. As I said, analyzer and polarizer are identical. They have given a name according to their use. If you use this crystal as polarizer, then it can be called also polarizer, and this can be called as analyzer. So what is the role of analyzer? Analyzer will help you to understand whether a light is polarized or not and what type of polarization you see. So look, if you have this polarizer upon like passing through this polarizer, the unpolarized light become completely polarized light. This is suppose this is linearly polarized light. Now you have analyzer, same identical crystal like crystal, but now at this stage you will see the same intensity. You look this at this situation, you will have the same intensity as you see here. So this is also I0 by 2, this is also I0 by 2. The same intensity you will see if the analyzer has its path axis parallel to the path axis of the polarizer. Now if you just rotate this analyzer about the incident direction of the light, then you will see the variation of intensity of the light which is passing through the analyzer. That means just after crossing the analyzer, if you rotate the analyzer, you will see intensity variation. Okay, intensity variation you will see. Observer will see different intensity than this one. Okay, so if you rotate this analyzer in its plane about this incident ray axis, then what you see, intensity will be intensity at this, say if you just rotate it, say at some time you will have intensity less than I0 by, so suppose this is I0 prime, which is less than, which is less than I0 by 2. Okay, less than I0 by 2. And further, if the crystal analyzer is rotated where, like at a position where the intensity, see the path axis of this analyzer is this one, which is perpendicular to the path axis of the polarizer. You look here, polarizer has path axis this way, and analyzer has path axis in this way. So these rays, these are actually parallel to this axis, right? So they don't have any component along the direction perpendicular to the vibration of their own electric field vectors. Okay, then you will see zero intensity here or no light. I hope you have understood why zero light here or no intensity will be seen here, because no light will be able to pass through this, since this light are parallel to, they actually pass, so they passes through this. If this unpolarized light is passing through this polarizer, you will get some intensity, at least half. Okay, and if the path axis of the analyzer also in the same direction or same, like parallel to, see path axis of the analyzer and path axis of the polarizer, if they are parallel to each other, then there is no intensity variation. But when you rotate the analyzer, you'll see intensity variation. So at 90 degree the intensity will be 0, at 279, 90 degree 270. Okay, at 270 also you will see zero intensity. Okay, so 270, so two places you will see there will be maximum intensity as I0 by 2, and at two other places intensity will be 0. Okay, so If the analyzer is rotated, then you will see twice very good intensity, twice in the sense at two different positions will be intensity 0. At two different portions of this there will be intensity half of the intensity. Okay, so this is how polarization can be, like light can be polarized, and also we can analyze whether a light is polarized or not. Okay, I think I'll stop it here for today. Tomorrow what I'll do, I'll just tell you why this, like mathematically how we can find out the intensity after passing many uh, this analyzer, or if you suppose you have your polarizer in this direction, analyzer along this direction, so what actually the intensity will be after passing through this analyzer. Okay, so that can be found out by Malus law. Okay, Malus law I'm not discussing today. We'll discuss it in detail tomorrow, and also we'll try to see another thing is that by scattering experiment, by scattering an unpolarized light, you can actually polarize that. Okay, so all right, so thank you for your patience. Bye for today.